Hello everyone and welcome to my lecture on the orthogonality of natural modes. This lecture will be relatively mathematical as I will demonstrate some mathematical properties of the natural modes. But we will need these properties for the real modal analysis of free and forced vibrations that I will do in later lectures. So think of this lecture as a bit of preparation for that. Okay. Let me start off by recalling the form of the equation of motion of an undamped homogeneous MDOF system. It looks like this, where M and K are the mass and stiffness matrices. Now, using techniques we have discussed before, we are able to derive the natural frequencies and corresponding natural modes. Now, let me just pick two arbitrary natural frequencies and corresponding natural modes. And let me call them omega I and ui for the first one I have selected, and omega j and uj for the second one I have selected. So these are an arbitrary selection of two frequencies. Now, what I will do is I will show you some of the properties that we can derive from this. For that, it's important to recall that because the natural frequencies and natural modes are determined from an eigenvalue problem, they satisfy the following equations. So minus omega I squared times m times ui plus k times ui is equal to 0. And similarly, minus omega j squared times m times uj plus k times uj is equal to 0 as well. Good, let me pre-multiply the first equation by, let me do that again, by uj transposed. So we have omega I squared uj transposed times m times ui plus uj transposed times k times ui is 0. And let me pre-multiply this one by ui transposed. So times uj, and also here ui transposed times k times uj. That is equal to 0. Okay. Now, for the next manipulation, I need to establish that m and k are symmetric matrices. And I will use that here, because for any symmetric matrix, then it holds that ui transpose times m times uj is exactly the same scalar as uj transpose times m times ui. And also that ui transposed times k times uj is the same as uj transpose times k times ui. So if I look at the two equations above, I see that in fact the stiffness term is exactly the same in both left and right equations. So let me subtract the first equation from the second. In that way, I get that omega I transposed, omega I squared minus omega j squared times uj transposed m times ui is equal to 0, because the term with the stiffness drops. Okay, so that means that if I look at this, that since omega I and omega j are not the same, for I and j not the same, so if I picked really two distinct natural frequencies and modes, then I must conclude from this that uj transposed times m times ui must be 0. Now, this relation, it's important, it's said that the natural modes are orthogonal with respect to the mass matrix. Now, if I substitute back this relation into either one of these, for I not equal to j, the first term will always be 0, and therefore we also need to conclude that uj transposed times k times ui is equal to 0. And that means that the natural modes are orthogonal with respect to m and k. So what does that mean? It means these relations hold in general. We didn't do any example. I did derive these for general circumstances. So that means that whenever you pick two natural modes that are not the same, and you pre and post the mass or stiffness matrices with them, the result will always be 0. That's a convenient relation. Now let's see what happens if I is j. If I is equal to j, then omega I squared minus omega I squared is already 0. So it means that uj transposed mui, which is then ui transposed mui, that is any, can still be any arbitrary scalar. So if we look back at these equation that I marked with the arrow, from that we can rewrite it that ui transposed times k times ui divided by ui transposed mui, that this is equal to omega I squared. Now this is also an important relation. It's a quotient, it's a ratio, and it basically says that if you pre and post the stiffness matrix and mass matrix by the same natural mode, this ratio will always produce the corresponding natural frequency squared. Okay, where are we going to use this for? Well, let me first, I want to discuss one more thing. It is important to realize that ui still contains the arbitrary scaling vector that we called alpha. So let me call this alpha I. Now what we can do, and that happens frequently in modal analysis, is what we call mass normalization of modes. And that is that we choose alpha I such that ui transposed times m times ui is equal to 1. And as a consequently, it follows that ui transpose times k times ui is then equal to omega I squared. So for this particular choice of alpha I, we can get it like this. Okay, where are we going to use this for? Well, let me construct the modal matrix that I will call capital U, which is the column-wise assembly of modes. So the first column is the first mode, second column is the second mode, and so on, and the last column is the end-of mode, like this. If I now look at the matrix multiplication U transposed times M times U, it follows that all the terms on the diagonal are in the form ui transposed M ui. So after mass normalization, all these terms on the diagonal, they will be equal to 1. All the terms that are not on the diagonal are 0 by means of the orthogonality properties. So that means that this matrix after mass normalization equals the identity matrix. And as a consequence, U transposed K times U will then equal a matrix with on the diagonal the natural frequencies squared, and all terms on the that are not on the diagonal are 0, because therefore you need to have a multiplication like uj transposed k times ui, and these are all 0. So this will be a matrix that I will call capital omega n squared, which is a matrix, diagonal matrix with natural frequencies on the main diagonal. So it's quite interesting, I would say, that these natural modes possess properties that if you arrange the modes in the modal matrix and do these multiplications, that these two diagonal matrices will come out. Okay, so this is, I would say, the general theory. Let me now walk you through an example. Where I will use this double mass spring system that we have seen before. And yeah, so this is M, and the springs are all the same. We have derived the equation of motion before. Equation of motion, that was M, mass matrix was 1, 0, 0, 1, times the vector of accelerations plus the stiffness matrix, and that was 2, minus 1, minus 1, 2, times displacements x1 and x2, like this. Okay, so we derived the natural frequencies, and we found that omega 1 was equal to the square root of k over m. The corresponding mode u1 is alpha 1 times 1, 1. And we found the second natural frequency, omega 2, to be equal to 3k over m. And the corresponding natural mode u2 was alpha 2, 1, minus 1. Okay, so let's demonstrate these orthogonality properties. I will first construct the modal matrix U, which will be then alpha 1, alpha 1, alpha 2 minus alpha 2. Okay, now let's compute a U transposed times M times U, and let's demand that this is the identity matrix. Okay, so U transposed is alpha 1, alpha 1, alpha 2 minus alpha 2 times the mass matrix. Let me put M in front because that is just a scalar, so I put M here. Then we have 1, 0, 0, 1 times alpha 1, alpha 1, alpha 2 minus alpha 2, like this. So this is just the mass matrix is in fact the identity matrix. So this equals simply like this, alpha 1 minus alpha 2. I can ignore this one, alpha 1, alpha 1, alpha 2 minus alpha 2. Now I have to execute this multiplication. So we have alpha 1 becomes alpha 1 squared. So we get 2 alpha 1 squared. Then for the second entry we have alpha 1 times alpha 2 plus alpha 1 minus alpha 2. So that is 0. Alpha 2 alpha 1 minus alpha 2 alpha 1 is also 0. And we have alpha 2 squared minus alpha 2 times minus alpha 2. So we have 2 alpha 2 squared as well. So we indeed see that this is diagonal. And we are able to produce the identity matrix from it if, in this case, alpha 1 and alpha 2 are the same, and that they are equal to the square root of 1 divided by 2m. Okay, so this is the normalization for the mass normalization of the natural modes. If we choose alpha 1 and alpha 2 to be the square root of 1 over 2m, then U transpose times M times U is the identity matrix. So let's see if now for this choice U transpose times K times U is the matrix of natural frequencies squared. Let's see if that is the case. So this is a K times alpha 1, alpha 1, alpha 2 minus alpha 2. Now we have 2 minus 1, 2 here. Alpha 1, alpha 1, alpha 2 minus alpha 2. So I will start at the back, so I will just quickly write down this matrix again. Let's see, we get 2 alpha 1 minus alpha 1, so that is alpha 1. Then we have 2 times alpha 2 minus alpha 2, so that is 3 alpha 2. We have minus alpha 1 plus 2 alpha 1, so that is alpha 1. And we have minus alpha 2 minus 2 alpha 2, so that is minus 3 alpha 2 here. Okay, so let's do the final one. So we have alpha 1 is 2 alpha 1 squared. Then we have alpha 1 times 3 alpha 2, alpha 1 minus 3 alpha 2, so that is 0. Alpha 2 alpha 1 minus alpha 2 alpha 1, also 0, as it should be, because it must be a diagonal matrix. And then we get alpha 2 times 3 alpha 2, and that again, so we get 6 alpha 2 squared. Okay, now let's substitute now the mass normalization in here. Then we get alpha 1 squared, that is then 1 over 2m divided by 2, so we get k divided by m there. And then this is 0 and this is 0. And then if we have alpha 2 squared, 6 divided by 2 is 3, so we get 3k over m here. And these are indeed the natural frequencies squared on the main diagonal. So this is correct. All right, so that concludes the lecture on orthogonality properties. I think the most important thing is that you understand these relations, and that you are convinced that indeed U transpose MU and U transpose KU will produce a diagonal matrix. Where we will use it for in terms of free and forced vibrations, that I will explain to you in the next video lectures. I'll see you there.